So, another type of reaction we're going to learn as we react with aldehydes and ketones is a way to take an aldehyde or ketone, and turn it into an alkene. Right? Turn it into a carbon-carbon double bond with this triphenylphosphine oxide. And a lot of people had a bunch of really good questions about this. So what drives this mechanism? Right? It's a good question. Like, why does this happen? Well, this bond is more reactive. This is pretty reactive. But also the phosphorus-oxygen bond is really stable. That's a really happy bond that oxygen and phosphorus both want to make. So that helps drive the reaction. Notice this thing is that word ylid, right, that I told you all about. And right here's some good confusing organic chemistry for you. Right here we have the negative charge and the plus charge on the phosphorus. This is assuming phosphorus acts like the way we want it to act, like obeying the octet rule, kind of not obeying the octet rule. And here it has, right, with 5 bonds. Here it has 4 and plus charge. I like to draw it like this ylid like this, because this makes me understand that carbon is really the nucleophile. And that's the part that's going to react with the carbon of the carbonyl and add in. Right? So these are like basic conditions again. What's the first step in a basic condition? Addition. Right? Addition. And then you make that kind of fun 4-membered ring. We'll talk a little bit about that. One thing to think about that I mentioned, and people ask this, the types of groups on the ylid affect the products you form. So EWG stands for electron withdrawing group. What are some examples of electron withdrawing groups? Oh, I would say if there was a ketone on the end over here, right? Another ketone. If there was an NO2, that's electron withdrawing, things like that. What would then EDG is electron donating groups. What could be electron donating? Well, an ester like this could be, right? Because now the oxygen is right there attached, right? That's electron donating. You could have an ether. I think that was the example I showed online in the video. Right? So anything that donates electrons. Halogens, I'm going to say, somebody had a really good question about halogens. I'm going to say they're pretty much always electron withdrawing. I'm not actually sure with the ylids how they work, but that was a really good question somebody to ask. But the cool thing is, if you have an electron donating group, you get a Z alkene. If you have an electron withdrawing group, you get an E alkene. Right? So again, tuning your ylid will give you different things, different products, an E or Z, as in Z same side. Good. So let's talk Wittig mechanism. So what happens here? The first step, right? It's like your nucleophile, like a basic conditions. It adds in, breaks the pi bond. You get this intermediate. Right? And the thing that happens is you can rotate, right? So this is still a sigma bond here, right? In a sigma bond, you can rotate around, right? And they both can rotate. And the way it adds in, you can get different E or Z geometry based on when these two connect, where are things in relation to each other, right? If this wanted to keep rotating, you could have R1 over here and R over here. So depending on when these connect, when this oxygen bonds to that phosphorus, that's how you can determine the stereochemistry there a little bit. Once you make this, now, right, oxygen loves phosphorus. That's going to break down really fast. Also break down fast, right, because that's a 4-membered ring. Pretty unstable, just bond angles, right? These are all sp3 hybridized atoms. That's a square. That's a 90-degree angle. That's less than 109.5. That's pretty strained. So it's going to happen fast. And you're going to break down and make the pi bond there. And you do a pi bond. That's the mechanism. That's why it happens that way. The phosphorus-oxygen bond and also that 4-membered ring intermediate is pretty unstable because it's a 4-membered ring. Another reagent that we're going to compare and contrast with the reagent we already know. We're going to compare this new reagent that's called this Gilman reagent with a Grignard reagent. So a Gilman reagent is copper with a negative charge. So it looks like this, attached to 2 carbons. So the negative charge is on the copper, but where is the electron density really at? It's actually on the carbons, right? They're the nucleophiles here, not the copper. So it's really these carbons are nucleophiles. How do we make these? So you get the lithium adds in. So you get this organolithium, then it adds in the copper, does like an SN2, right? Where you have your copper iodide. This comes in and knocks that out. You get two of them on there eventually. So that Gilman reagent, the cool thing about this is if you have this alpha beta unsaturated ketone. Whoa. So let's just talk about that. So we have this situation. If you just look at this, so you have the same starting material. Here's this Gilman reagent, and here's a Grignard, which you know. Where does the Grignard go? The Grignard goes to the carbon of the carbonyl group, right? It adds in right there. Boom. Where did the Gilman reagent end up? It ended up down here, right? That's a 1,4 addition versus a 1,2 addition. So that's the difference. If you want to add something to this position, this 4 position or beta position, right? We talked about this is considered alpha. Oof. This is considered beta then, right? This is also an alpha carbon. The numbering wise, 1, 2, 3, 4, right? It's kind of like that. This is the p orbital system. You can think about the resonance structures here. Maybe I'll show you that in a second. Right? These are all lined up. They can do resonance. So an alpha beta unsaturated ketone is a ketone, alpha beta unsaturated, meaning it doesn't have hydrogens on there, right? It's not saturated with hydrogens. Alpha beta unsaturated. A Gilman reagent adds into the 4 position, and a Grignard reagent adds into the 2 position. Gilman also, something they call this a beta addition, or they call it a Michael addition. So a lot of names here for the same thing. You have conjugate addition, 1,4 addition, a beta addition, or a Michael addition. And no, it's not named after me. Okay, so it reacts differently. Different reagent reacts differently. That's nice because it gives us a different position to add. 1,4 instead of 1,2. Now, let's double check our understanding for why is the beta position even reactive? Let's draw some resonance structures to remember, right? So a resonance here, right, could be pushing electrons up towards the oxygen, right? The oxygen is more electronegative. It's going to pull those electrons up. So which atom now has a plus charge and which one has a minus charge? The oxygen should have a minus charge, and carbon 4 down here should have a plus charge. Now again, these are resonance structures, right? Let's do our numbering again. 1, 2, 3, 4. Or we could say 3 is really the same as an alpha, and 4 is the same as a beta carbon, we call those things. So you do those resonance structures to understand how this might react. Right, so this resonance structure tells us that the 4 position, the beta position, in these alpha beta unsaturated carbonyls is actually electrophilic, and that's one of the reasons why things will add there. Okay? All right, so now let's actually answer why this happens. So resonance makes sense. Why is Grignard different than copper? Why is magnesium different than copper? So this is a somewhat of a theory of hard soft. So if you think about the carbon here, carbon 2. Carbon 2 is directly bonded to the oxygen. That's probably the most electron deficient one, right? If you had to ask yourself, what's more electron deficient, carbon 2 or carbon 4? I would say carbon 2 because this is the one directly bonded to the oxygen, right? So that's more electron deficient. And if I looked at a Grignard versus a cuprate, this Gilman reagent, a Grignard, this R is really like a carbanion, right? For this one, it's really like this. It's really much more of a ionic bond. So a Grignard is much more reactive. And so you're kind of matching reactivity, right? Grignard is hot. It is reactive. It's going to react with the most reactive site right away. And so Grignards will choose the most reactive position. A cuprate, a Gilman reagent, is a little less reactive, right? It's a little more toned down. And it's actually going to react with the less reactive position as well. There's even a further understanding of this where this copper actually coordinates to form a 6-membered ring. And that's why the copper actually adds the 4 position as well. But again, so we're kind of matching reactivity. Grignards are super reactive. They're going to react with the most reactive site. Gilmans are a little less. They react with a little less site. And the copper can make this 6-membered ring coordination kind of thing, which also helps deliver it to the 4 position. So the mechanism here, to recognize this is a Gilman reagent. We're going to do that beta addition, that conjugate addition, that 1,4 addition, or that Michael addition. Here we go. That adds in 3 arrows. 3 arrows for, so this is an addition. That gets us to this enolate. All right, let's renumber those carbons and atoms. 1, 2, 3, 4. Only adds in once, so this is this enolate. And now we're done. Right? There's nothing really else we can do. So now we add in the H plus, and the way this works is very similar to the enamine. Right? You did the enamines that break down. The electrons come here, and the pi bond reacts there, and that gives us this. So that new H is right there that got added. This is not a catalyst, H plus. That's how it works. Step 1, step 2. So addition, and then of course, protonation. Right? Make sure you get the proton on the right atom. You could have protonated here. Right? You could have protonated on the oxygen, but then what would you have to do? Ta-ta! Merization. Which is fine too.